It's my great pleasure to also introduce the second speaker, Christoph Belak, who has also done very inspiring work on stochastic optimal control. But actually, I think most of the audience don't need an introduction because he has actually been here in KAUST last year at the workshop. He's my good friend and colleague from Berlin. And today he will tell us about branching diffusion representations of nonlinear PDEs. Please, Christoph, go ahead.
Thanks a lot, Christian, for the nice introduction. Yeah, first of all, I'm very sorry that I couldn't make it. I would have loved to be at KAUST. But yeah, I have things to take care of, including a little daughter here in Germany. So it has to wait until next time, until I can make it back to KAUST, I hope at least. So today's talk is about, well, branching diffusion representations. Most of the talk will be about a paper we wrote a couple of years ago, actually, with Daniel Hoffmann and Frank Seyfried from the University of Trier. And yeah, well, I really like the idea behind these branching diffusion representations. We learned from that paper that in applications it has certain shortcomings. And since then, I haven't looked much into that anymore. Until recently, when I had a student, Lotte Schnell, who wrote her master thesis with me, and she looked into a slight variation of that problem. And she had very promising results. And while it's not on a level that I can present it at an international conference yet, these results are really interesting, and I want to at least give you an outlook. I think this might open up one or few doors in that field. Before we get to branching diffusions, let me first motivate everything a little bit. So the long-term goal, which I'm interested in, is numerical methods for nonlinear and especially non-local PDEs. The reason just being that I've worked in stochastic impulse control for a while, and the PDEs associated with those problems, they are nonlinear, non-local. So you see here an equation, PDE that arises in stochastic impulse control. And those I would like to solve numerically, yeah, if possible. So let's have a look at this equation. What does it involve? It has two components. The first component here, this is nice. You have a partial derivative with respect to time, and then an infinitesimal generator. So a second order linear PDE operator here in this setting. So the first component is nice, yeah, a nice linear PDE operator. The second component makes it a bit more tricky. So U is the solution, but M of U is a non-local operator, meaning that if you look at the PDE at a point X, it evaluates U at a different point Y. Yeah, this makes this thing non-local. And yeah, as I said, this is linked to stochastic impulse control. There's no need for the sake of this talk to show you this connection, but it arises in this field. And of course, if you study this kind of things, then you would also like to compute a solution eventually. Yeah, and this is what this talk is at least based upon. Yeah, so formally looking at this kind of PDE, it is fully nonlinear because you have this maximum here. It is non-local because of this operator M that you see here. It has a free boundary, which just means that you don't know in which region this operator here is active and in which region the other one is active, and the boundary which separates these two regions is unknown as part of the solution. This makes this a free boundary problem. Then I'm interested in problems from finance, and for those, the infinitesimal generator might degenerate in the sense that the coefficient in front of the second order derivatives might become 0. Yeah, so very little regularity in the solution of the PDE. And I don't want to restrict to one-dimensional problems, but also want to solve it in at least moderate number of dimensions, right? 2, 3, 4, 5, maybe would be interesting. And then, since this is motivated by impulse control, I don't want to compute U just at one fixed point, but if possible, on an entire region because this tells me something about the optimal control. That's the long-term goal, at least, and we won't be able to do that in this talk with the methods that I'm presenting today, but just as a motivation, these kinds of PDEs are interesting for some people, and so we want to solve them numerically. The PDE that you see here doesn't fit into the framework that I'm presenting, but what you can do is, and what you usually do in most of the numerical schemes that use, you regularize the PDE, or you look at the penalized version, where you just take the linear part and the non-local part, and you penalize the non-local part with the parameter lambda. And if you send lambda to infinity, this formally converges to the original PDE. And the regularized one, which you see below, this does not fit 100% into the setting, but it can be fit into the setting that I'm presenting next. So we have a linear part and then a nonlinear part, which involves a non-local operator. And this is the kind of thing that I'm interested in. Right. How would you do something like this numerically? What can you do? So first of all, it's a PDE, so you can look at classical PDE techniques, apply finite differences to the to get an approximation of the derivatives, and then you will have a maximum involved somewhere in there. You can use a policy iteration to handle that. And these techniques are used. This is something which works, which does converge, which is known to converge. And it works, I would say, reasonably well. We had a short look into that when we applied it to a problem from finance. It works well in 2 dimensions, 3 dimensions maybe. But one issue that we had and realized is that always with finite differences, you approximate on a bounded subset of the entire state space. So you need to impose artificial boundary conditions there. And the numerical scheme is very sensitive to that because of the non-local operator. This has to work very well together if you want these kind of things to work well. Yeah, but that's certainly one thing that one can do numerically. Another thing is to go away from continuous time, but go to discrete time instead, look for a nice approximation in discrete time. And then it's just a classical Markov decision process, because in discrete time, everything is an impulse. Everything is impulse controlled, and then use classical techniques from there, which essentially boils down to policy iteration again. But this would certainly also be feasible to do. Next thing that you can think about is since the PDE is linked to a stochastic control problem, it has a stochastic representation. So you can express it as an expectation of something. And once you have a form like this, you can try Monte Carlo, which doesn't work directly, but you can, with a few tricks, probably get that to work. I wouldn't bet on very efficient schemes in that situation, however. Other than that, you could look at more recent things that have been done. So if you're following the literature on numerics for PDEs, a big field which has opened up over the last couple of years is deep learning techniques. So you try to approximate the solution by a neural network. This certainly works for a lot of PDEs. I'm not aware of anything which fits into this stochastic impulse control setting, but that's something we are looking into at the moment. And this might work. I'm fairly confident that we will get something reasonable out of this. Or reinforcement learning, since this is a stochastic control problem, you could, of course, apply reinforcement learning techniques. But I have various reasons why I don't think these are your first methods of choice. If you've been there last year when I gave an introduction to reinforcement learning, you probably know why. Yeah, that's nothing for today, at least. And there's more that you can do. And one thing that I would like to present today is a scheme, a numerical scheme, which is based on a branching diffusion representation of the PDE. And this leads me to the overview for today. So I spent most of the time showing you how these branching diffusion representations work so that you get a good understanding of what's behind it. Then we will talk about theoretical results, convergence, or actually just proving that these representations work. Then I have a numerical example for you, and then in the end, a little outlook. We will discuss the issues that you run into when you try to apply this in practice, and a few ideas, or one idea how one might be able to mitigate that. All right, but most of the time will be spent on the branching diffusion representation. Since I know in this workshop there are a lot of young people, I think it's a good idea to actually stick to the basics for as long as possible, and then maybe motivate you to look into these kind of things if they're interesting enough for you. So how do these branching diffusion and representations work? Let me start by the kind of PDE that I'm interested in. It's slightly different than what you saw before, but nevertheless, you still have this linear component, time derivative, infinitesimal generator. And then you have a non-local term over here. It depends on t, it depends on x, and it depends on the entire function u. So f might evaluate u at other points than just t and x. So to be precise, the first one is an infinitesimal generator, first order derivative, second order derivatives. So nothing special about this one. I should, however, say a few words on the nonlinearity. As I said, this will be a non-local term. And for the sake of this talk, I will just assume basically two things. That the non-local part basically comes from an integral. So I can even express it in terms of an expectation with respect to some random variable delta. Think of it as just an integral. It integrates all possible values of delta according to some probability distribution. And the second underlying is basically that the dependence of f on this non-local component is analytic. So you have a power series expansion in the non-local term. So this is the just switch. So the I that you see here is a subset of the natural numbers, and then you have this power series expansion basically here with coefficients ci. So basically analytic in the nonlinearity and the non-locality, and the non-locality is of a specific type of integral type. So that's what I want to look into. All right. First thing to do is I claim that this has a nice Feynman-Katz representation, and this is our starting point for looking into these branching diffusion representations. So how do you get towards the Feynman-Katz representation? The first thing that you do is you write down the diffusion associated with the infinitesimal generator that you see here. It has standard form, drift mu, volatility sigma. Nothing fancy about this one. And then, at least informally, ignoring any integrability conditions, you can show that this kind of representation here holds. How would you do that? Assume you have a classical solution of the PDE, then you can apply Ito's formula here, express it from time t to time 0, and the infinitesimal generator shows up. And since u is a solution of the PDE, you can replace the infinitesimal generator and time derivative by the non-locality or nonlinearity. And then that's what you end up with. That's the kind of expression that you get. That's just Ito's formula, taking expectations, assuming that the local martingale that shows up in Ito's formula is an honest martingale, and then you have it. And then in the next step, I have an explicit form for my nonlinearity, so I may just plug that in, write down this power series expansion, and the expectation can be pulled outside and combined with the expectation that we have outside by linearity. So formally, this is what you get. All right, and from here you see that the naive Monte Carlo is maybe not what you would want to do. So maybe let me draw a picture. This is the representation that we have right now. So if you want to do Monte Carlo, what you need to do is to evaluate this expectation. You need to simulate the diffusion. You start here somewhere at time 0, get your diffusion up to time capital T. And then since we have this integral here, you have to evaluate it basically at every point S in time. Or you should approximate the integral anyways, but you will need to evaluate the diffusion at many points. And even worse, you always have this function u, which is the unknown. So you would end up with a nested simulation. At each SXS, you still need to do another simulation to get the value of u that you need in your integral. So that's why naive Monte Carlo here is not efficient. It's not the thing that you would like to do. But what you can do is you can simplify things, or you can rewrite things to make it a little bit nicer. And this is what I want to show you. The first thing I will show you is how to get rid of this integral here, so that we don't need to evaluate the process at any point in time, but just at one point. That's something that can be done. And this is done via randomization. So what you see here is, again, still the same Feynman-Katz representation from before. And now what I do is I multiply by certain things and divide by them. So regarding the first term that you see here, I multiply that by f of t and divide it by f of t. And f of t is what you see here. It's the tail of the cumulative distribution function of some stopping time, which has a strictly positive density. Why? You will see in a second. This density is denoted by rho, and rho I also plug into the integral. And in the integral, you can see that this is possibly a good idea, because now what is happening is you're integrating something with respect to the density of that stopping time. And that something is what you see here. And if I assume that my stopping time tau, which is where this density comes from, is independent of everything else, so the Brownian motion driving the problem, then I can just integrate that out, right? Disintegrate it, and I end up with this. So I find it easier to read it from bottom to top. If you want to compute this expectation, the expectation of that sum, how would you do that? You're just integrating with respect to the density of tau, and everywhere where you see tau, you replace it by S. That's how this is done. And you can do something similar for the first part, for the first component here. If you want to compute the expectation here, or you want to disintegrate tau, what do? You just integrate with respect to its density. So everything from capital T to infinity, that's precisely the f capital T. And now this already looks a bit nicer, because now I don't have the integral anymore. I only need to compute my unknown function u at that stopping time tau for that value of the process at that time tau. That's, at least formally, this looks a little bit easier. Still, it's a nested Monte Carlo, so and not quite what we want. But at least it looks a little bit simpler. Next thing I'm going to get rid of is this sum that you see here, basically by the same idea. Sums are just integrals, just with respect to a counting measure. So I can do the same trick, and this helps me get rid of, this is possibly an infinite series here, so I can simplify that even further. How can this be done? Same trick. I multiply by strictly positive probabilities and divide by the same. So this doesn't change anything. And now I can treat this as, well, an integral with respect to a discrete measure over here. So if I take a random variable I, which takes values in this set curly I here with probabilities given by pi, then if it's independent of everything else, I can just integrate that out. I get rid of the sum, and I just have to evaluate everything at that random variable. That's certainly something I can do, and now I got rid of that sum. Already looks a bit nicer, right? Let's see. Yeah. Okay, and this is essentially the first step in the branching diffusion representation. I like to call this the branching diffusion representation in the first generation. Why that you will see in just a second. Yeah, so let's maybe go back to a drawing board. So here's capital T. If I want to do Monte Carlo for this thing over here, what do I need to do? I still need to sample the diffusion. So let's draw diffusion like this. And where do I need to evaluate that diffusion? I need to evaluate that at capital T and at time tau. Yeah, so let's draw a random variable tau. Maybe it ends up here. And then all I need is basically this point. I don't need the entire path anymore. And I need to compute the value here at capital T. So this already feels a little bit easier. And if I'm lucky, my random variable tau is strictly larger than T, then I am in this situation. It's something that I can compute fairly easily. It's more complicated if tau is strictly less than T, because then I'm in this case over here. And here I still have the unknown function u. Yeah, so I still have a nested simulation here as well. Yeah, so let me draw that, what you have to do. So if tau is strictly less than T, then at this point that you see over here, you have to compute u. And if you want to do that with a nested simulation, you would go ahead and draw more Monte Carlo samples from here to compute that. Yeah. And this is very expensive because you're not just drawing one black path, but 10,000, 100,000. And then for each of those paths, you need a certain number of red paths. This is still quite costly, but at least it feels already slightly better. And we can improve on that. We can do that even better. And this is the idea behind these branching diffusion representations. So this is where we're at. And now what I do is I look at this term over here, and I will rewrite it slightly. The way that I do is I draw this random variable I, and this is just a natural number, and then I look at independent diffusion processes, which I call XL. And so independent of the original Brownian motion and independent of all random variables that we've seen so far. And I start these diffusions in the point at time tau in the point X plus this additional delta that was showing up here. Yeah, so in the point that you see here. And then, since in law, this is still the same, right? Initially, these XL tau, they have precisely this value here. So I may rewrite this power, u to the power I, as the product of these u XL, of my new diffusions that you see here. And now what I can do is, here for each of these, this is really now just the original u that you saw before, just started in a new point. And I can do another representation, Feynman-Katz representation like this. So it gives me expectation. I have to condition on everything that I have. I should condition on those probably. But then I get basically the same representation as we have here, just with a new starting value, x tau plus delta. And since everything, so I have that for each of those, that's a product of these conditional expectations. And since all of them are independent, product of the expectations is the expectation of the product, and I can bring the product inside. Everything that you see in front is measurable, right? So I can also pull that inside, and then my big expectation outside eats up the conditional expectation. So that's how I get rid of the expectation that shows up in here. I can just push that into this expectation over here. So if you do that in the picture, what this means is, here's capital T, I draw my random variable tau, I draw my process X, right? But only up to time tau in this situation. Then at time tau, if you recall, I'm looking at x tau plus delta. So this causes a jump, let's say, to this point over here. And now what this expression here tells me to do is to do the same thing again, but starting at this new point, this red point that you see here at time tau. And I do that for L equal 1 up to L. So basically, I'm drawing a new diffusion, which I do in green. This is maybe x1. And this I evaluate up to time tau plus a new random variable, a new stopping time tau1. So just the same thing, but started in the red point. That's for L equal to 1. I can do that for L equal to 2. So that goes up to tau plus tau2. Another independent stopping time. And I do that all the way also for x, the largest one is xi. This goes to tau plus tau I. And now you see the branching diffusion that I'm interested in, or that helps me represent my expectation. So initially, I start with a single diffusion, x, that's the black one that you see over here. And then it lives up to time tau. Then I have a jump, which takes me up here. And then at that point, my diffusion branches into these I subparticles, new particles. And I repeat the same thing for all of those. They also live up to another stopping time. And at those stopping times, they will have another jump, and then you branch off again, and eventually you will reach time capital T. And at time capital T, the U no longer shows up, but it is replaced by a G, and then you get that representation. So you just repeat this kind of randomization by independent random variables over and over again. And if you do that, then the final object looks something like this. Essentially, it's an expectation of something, and that something looks like this. What precisely is that? Let me explain that for you. So the first product that you see here, this goes through all particles done or constructed in the way that I've just explained. These are all the particles which are still alive at time t. So the ones which make it up to time capital T. For those, you evaluate G at that location where your diffusion is at, and you normalize that by this tail of the cumulative distribution function. The second product is over all of those which are which do not make it to time capital T. So that's all of those which are alive before or at time t, without those which are alive at time t. So only the ones strictly before capital T. And for those, I evaluate this function C and normalize it by the densities and the probability mass function that I have. And that's just, as I said, is repeatedly doing this randomization by independent random variables and plugging that.
I'm sorry, Christoph, I think we have some problems with the connection.
And that's the random diffusion bandwidth, right? Do you still hear me?
Yeah, sorry, Christoph. I think we have internet connection issues.
Who? You or me?
That's a good question.
It's not me.
But now actually it seems better. Maybe we can
seems better.
continue.
Okay. Then let me just.
I know. Now that we said it, no, it's not better.
Very quickly. So basically,
yeah, sorry. Is there something we can do? Could
I
you
don't see anything at the moment? I'll just do you still see me?
Do we still see him? Okay,
Just
our
wait.
connection seems to be
Christoph's
good. I'm
connection,
being
because I
told.
can hear you, Christian.
You can hear.
Okay, perfect.
Okay.
Thank you.
Okay.
Right. I mean, Christoph, if you're still sharing your video, maybe you can stop doing that.
Yeah, I can try.
Okay.
So it does not show any connection issues, but if Nizar doesn't hear me, I think Nizar said he can hear Christian, but not me.
I do hear you now.
So
Okay.
you can hear me now.
Now
Okay, perfect.
now it's better. So maybe we can just try again and restart at this point. And I will let you know again if you know.
Yeah, just let me know, and then
So
we'll pick up.
Raul just says we will restart, but without branching. So
Yeah, precisely. So then let me maybe pick up here at this terribly drawn picture. So basically what you do is you start with one realization of your diffusion, up to some stopping time tau. At that point, it branches into into I subparticles, where you restart, do the same diffusion again, but independently. They all live up to the new stopping time, tau1, tau2, up to tau I, and you repeat that until you omega-wise reach time capital T. And then you collect all the terms which show up in between in your expectation, and this is what you end up with. So the first component, these products here, these are all particles which make it to time capital T, whereas the other ones are those which die before, where the stopping times are strictly smaller than capital T. And you just gather everything into a nice random variable, and then take the expectation, and this should be, by the arguments that I've just shown you, should be the solution of the PDE. Because I've done nothing fancy except randomization and integrating independent random variables, so this should work, right? And what is nice about this allows you to now do Monte Carlo in a forward sense. You just have to simulate this branching diffusion, evaluate it at the branching times, and then you can compute this random variable here, and do the usual Monte Carlo stuff. And that's the main idea about these branching diffusion representations. What you've seen here is certainly nothing new. That's nothing that we came up with. So let me give you a brief overview of the literature. The first time this shows up, at least as I'm aware of, is McKean in the 70s for a very particular PDE, which has already a really nice form where you can basically see that it wants to branch. But then it took until the 2012 is the first paper where this is studied in the setting of doing or with the purpose of doing Monte Carlo for PDEs. So Pierre-Henri Labaudet was the one who rediscovered this basically. And then there's a paper by, again, Henri Labaudet, with Han, Lisa Tusi, and they look into this much more detail. So this is basically these two papers are the starting point of the now modern branching diffusion theory, I would say. And they look at the situation where your nonlinearity depends just on the function it's analytic in the solution of the PDE, zeroth order case. There's an extension to first order case. So you have the first order derivatives showing up in the nonlinearity. That's this paper over here. And further extensions in all kinds of directions, elliptic PDEs. There is situations where you only have local analyticity or Lipschitz nonlinearity. This can be handled to a certain degree. And what we did is just realize you can also do that for non-local operators. So our contribution is just the jumps, but the main idea is they go certainly back to these works over here. All right, and there's more. There's probably not a complete list of what is going on. Okay, that's the main idea. I hope that you more or less get what is behind this. And now the question is, what does the theory tell us? Does this really work? Is this good? Can we say anything about Monte Carlo? Should Monte Carlo work? In which situations does it work? When doesn't it work? Yeah, so let's look at theoretical results. And the first thing that you should do when you write a paper on this is check that the derivation that I just showed you actually works if everything is nice enough. Yeah, so suppose we have a classical solution of the PDE. You impose some integrability and growth assumptions so that everything that I've just shown you basically works. And then you verify so that you can represent the solution of the PDE in that particular point 0x in terms of the expectation of this random variable that you see over here. And there's not much to the proof except that you go through the slides which I have just shown you and you verify that everything I have done works under these integrability and growth assumptions that you see and that you don't see, which I'm hiding from. But that you can make the arguments that I've just shown you rigorous. And this is a good first result, but this is probably not the most interesting one because this is not very useful in terms of numerics, because in terms of numerics, you want to go the other way around. You want to define a function in terms of this expectation, and then you want to verify that it solves the PDE, right? Because that's what you do numerically, and what you do numerically should satisfy the PDE. So let's look at it the other way around, and let's see if one can show that. So what I'm doing differently now is here in this random variable, I'm starting everything at time 0 in the point x. But of course, I can also do that at a different initial time, small t, with a different initial value, possibly x, and for all of those simultaneously. It gives me a new random variable for each initial condition tx. And then I define a function in terms of that expectation. And then again, under some most of the integrability and growth assumptions are natural, in the sense that they are not surprising and not really strict, not very strong, except for one, which you will see in a second, which is spelled out here. But if you impose enough conditions, then you can show that if this function, defined like this, actually solves the PDE in a weak sense, in the sense of viscosity solutions, which for us is good enough, because we know how to prove uniqueness for viscosity solutions in many cases. So that's the result that you want. It tells you that if you do Monte Carlo, if you compute this expectation, then you have computed your solution of the PDE. The tricky assumption that you see involved here is this one. So for each tx, I look at a small ball of size epsilon around tx, and all of these random variables simultaneously. So all psi sx, with sy, sorry, where sy is in a ball of size epsilon around tx. And those I want uniformly integrable. This is something which is needed so that you have enough regularity in here so that you can actually link it to the PDE. You need to look in a small neighborhood of your point tx. And then the question you might ask is, well, is that a strong assumption? Is that not a strong assumption? Can we make sure that this works? Can anything be said about this uniform integrability assumption? Maybe you want even more, since you want to do Monte Carlo for this. Maybe you want this to be an L2, so that you have a variance and then you know how well your Monte Carlo performs. So maybe some LP estimate would be nice to have. And I should say a few words on the proof. I shouldn't, because it's just going through the slides backward. You do the representation the other way around, and then you have a Feynman cuts representation, and then one knows how to proceed from there. That's also standard. But what you should really ask yourself is, what about the integrability of this random variable? This is important for the numerics. that you want to do. And here's the result that we have. This is basically a direct generalization of the or direct adjustment of the results in the 0th order case. So the paper by Orila, Bodea, Tan, and Tusi, just with the jumps in there. So what you can show is you get that these random variables, the set of these random variables is bounded in some L kappa space, kappa larger than 1, under either of two conditions. Either, this is the simple one, you have constants C1 and C2. C1 needs to be normalized, you take the maximum of those, and if that's less than 1, then you have your integrability. What is C1? What is C2? So C1 involves basically, again, this tail of the cumulative distribution function and the terminal condition. So that's the maximum norm of the terminal condition. So the terminal condition should be bounded, is what it tells you, and it should be very, very small, so that this thing here can be smaller than 1. And the second constant that you see here, C2, is basically on the coefficients in your power series expansion, normalized by the density of the stopping times and the probability mass function of the random variable, which gives you the number of branches. And again, these should be small. They should be less than 1. If that's the case, so if everything is small, then you have integrability up to arbitrary order, essentially. Or you can get integrability, even boundedness in LP, which is great for Monte Carlo, for error estimates. This is a rather crude estimate here, or crude condition. You can refine that. That's the second part of that theorem. What you want is you look at the power series where you replace the coefficient Ci by its sup norm. And then you want this to still have infinite radius of convergence. Then you can write down this integral over here, where that comes from. I will show you in a second. And then you want that your time horizon is smaller than that integral. So basically that tells you that if the time horizon is small enough, then it works. Then you are good to go. But still you need some boundedness, uniform boundedness of everything involved basically to make that work. And there's not much that we see how these conditions can be improved. And frankly, they are a bit discouraging because they tell you you need a very small time horizon, or the data of your problem needs to be very small. So the number of applications is limited by these things. Especially second one, if you have a larger time horizon, then nothing you can do. So let's discuss them in a bit more detail. Maybe also the proofs, because this is useful to understand where that comes from. Because this tells you if you can improve something or not, and how much room there is for improvement. Let's look at the first situation. So suppose that here holds. Why do we get this integrability? It's fairly simple. You look at these random variables here. So you take your psi, take it to the power of kappa, and then you want to take expectations. And then you may recall that these psi are basically long products. And then each factor in that product you can bound by this term over here. Since everything is less than 1, the entire product is less than 1, and then the expectation of that is also less than 1. So that's just a very crude estimate of the components of that random variable. That's how you arrive at that one. And that's also why this is a very crude condition. The second one works slightly differently. Instead of bounding the random variable by 1, we bound it by another random variable in a clever way. This random variable, the upper bound, is constructed in a way so that you can interpreted as another branching diffusion representation of an ordinary differential equation. So that's an upper bound now given in terms of an ODE. And then you just ask yourself, does this ODE blow up or not? If it doesn't blow up, then you have a nice finite upper bound and you're good. If it blows up, then you're done. And the condition that you get for blow up is precisely the condition that we've written down here. So if the time horizon is small enough, the ODE doesn't blow up. And this is, in fact, necessary and sufficient. So there's not much room for improvement here if you go this way. And that's why, I mean, I really, really like the idea. I think this is very clever, these branching diffusion representations, but these results are a bit discouraging, at least on the theory side. And the issue is that even in applications, sometimes applications work better than the theory, but at least in what we have learned over the last years, or when we looked into this, was that there is not much room. So this really is an issue. The integrability of this random variable psi tx just is terrible in many situations. So this shows in practice. Nevertheless, I have a numerical example for you, and we will go quite quickly through that because even though I said that this is discouraging, I still think that it is worthwhile to look at these branching diffusion representations. There are many examples where this should be your method of choice. If it works, then from what we have seen, it works really well. And it's a nice way to solve high-dimensional, possibly, PDEs, which are nonlinear. So that's by itself something very great to have. It's just that you have strong assumptions to impose on your PDE to actually guarantee convergence. And here is one situation which I think is very very encouraging because it's a nice problem from finance, so it's an application, and I don't see many other ways of solving this kind of thing in such an efficient way. So it's an example inspired by the 3 papers that you see here. Basically, it works in the following way. Suppose, so we're doing math finance now, and you have an option, you hold a position in an option, European option, G, which is written on some underlyings X, that could be multidimensional if you want. And the counterparty, so where you buy that option from, say a bank, is now assumed to be defaultable. So you have a credit risk. And in addition, we assume that it is systemically important. So it's a large bank, but it may go bankrupt. Now, what happens if a large bank goes bankrupt? This has a ripple effect on the economy. So this drops the stock of the bank to 0, right? It has defaulted, but since it is systemically important, it also affects the prices of the underlyings. And this shows in the valuation of that option. So if the bank defaults, it has an impact on the prices of the underlyings. There's a jump in there as well. And if you then do risk neutral pricing, the way that it works is, so tau is the default time of our bank. And if it survives until maturity, then it's just your usual risk neutral pricing formula. You discount the payoff under risk neutral measure, which I'm hiding here. And then you have your price. And if it defaults, what do you do then? Then you get a recovery value. So if it has a positive value, you get a fraction of the value of, well, basically a copy of that option, which is also with respect to another systemically important counterparty, with the only difference is that it hasn't defaulted yet. That's how you price these kind of options. So basically, it's an identical thing. You just assume that it hasn't defaulted yet, and what would be the value then? And then you see in here, straightforward Monte Carlo is tricky, because if you want to compute the price at time t, you need to know the price at time tau at time of default. So that's a nested simulation, and not what you want to do. But you can write down pricing PDE for this thing. And it turns out that, I won't show you how, but it turns out that if you approximate this recovery value function by polynomials, then it fits into this branching diffusion framework. And in our paper, we did precisely this on a one-dimensional underlying X. And then the referees told us, please do it 500 dimensional or higher dimensional, because apparently that's more important. And still works. Yeah. So what we looked at is a European put, yeah, on a basket of 500 underlyings, or 499, I should say. And yeah, try to see if that works, and it does work. Yeah. So this is one application where I think branching diffusion representation should be your method of choice. And here is the numerical result. What you see here is the following. So this here is the price of the option, and we've plotted it against the intensity of default. Yeah? So tau has an intensity lambda, default time has intensity lambda, and we plot that from 0 to 0.2. And then we plot three things. The black one is where your counterparty does not default, so that should always have the same price. Then the green thing is where your counterparty may default, but is not systemically important, meaning that if it defaults, the underlying prices are not affected. And then the last one, the red one, is the example which I outlined. So you have a counterparty which may default, and if it defaults, it affects the prices of the underlyings. And then you see the price going down quite rapidly. Negative prices here, because that's a short position, I think, in that example. Okay, and what you can learn from that is, first of all, well, the method works, yeah, even in applications. And from this picture, you can also read off, which I think is quite nice, how large this systemic risk is, right? Because we have the price without default, we have the price with default, and we have the price with default and systemic risk. And then you can ask yourself how much of the credit spread does the systemic risk make up, and how much the credit risk. Yeah, so basically the difference between here and the difference between here, you see that the systemic risk component is much larger. Yeah, so the main threat is the systemic risk of your counterparty and not the default itself. So that has a high impact. And if you think that your counterparty is systemically important, you should take that into account. So that's what you can learn from that. So, yeah, short outlook, very short outlook, since time is running out anyways. So as I said, the main issue with branching diffusion representations in applications is these strong assumptions that you have to impose. And this is something that, as I said, we were not so happy with, but we didn't see any way on how to improve this. And I think if one is able to improve that, this would be a big step forward in that field, and it would be great if someone has a way of doing that. And you can start thinking about what you can do, or what the reason is that you need so much such strong assumptions. And for me, it's the problem is that there's so much randomization. Every time the diffusion branches, you introduce new random variables. So the final thing, the final random variable that you want to simulate, is just not interpretable anymore. Yeah, in many cases. Yeah, the number of branches might be unbounded. The number of particles that you have in each branch might be unbounded. There's randomness in the diffusion, and you have so many independent copies of that. So there's too much randomness involved. And here's an idea, which apparently seems to work. So basically, I haven't looked into the branching diffusion thing for quite a while. The paper that I presented is published in 2021, I think. So since then, we haven't looked into this anymore until I had a student who wanted to look into that for her master thesis. And I just gave her what I thought would be a simpler setting. So instead of looking at a PDE, I told her to look at an approximation of that PDE. Yeah, think finite differences. Yeah, do a finite difference approximation of the PDE. And then this is well established. These finite difference approximations, they also have probabilistic representations in terms then of Markov chains instead of diffusion processes in continuous time. And we have a well-established convergence theory for finite differences. So the viscosity theory tells us that whenever you have a scheme, a numerical scheme, which is monotone, stable, consistent, then converges. Yeah, so let's pick something like this, like a finite difference scheme, and try to do the branching diffusion approximation for that. And we're still experimenting with that, and we are still in the process of writing everything up. But the results that she got in her master thesis, they were surprisingly nice. So what she was able to show is that so if the nonlinearity is not too wild, which you can quantify basically by looking at its power series expansion or variant of that. If that's nice enough, it has a nice infinite radius of convergence. And if you balance your spatial grid and your time grid in a suitable way, then this strong integrability assumption is always satisfied. And yeah, so you can get rid of that strong assumption because you may basically push that into the time grid. Yeah, if the time grid is nice enough compared to the spatial grid, yeah, for that particular finite difference scheme that we wrote down, we realized the strong assumption is gone. Yeah, and this was, I think this is really interesting, and we're still looking into that. So yeah, for the next talk, I might be able to present you the full results of that, but this looks very promising. And it has certain implications, which I can already talk about. So, of course, we are now not solving the PDE anymore, but the finite difference approximation. Yeah, but one of the advantages of this branching diffusion framework is that you don't care too much about the dimension of the underlying process. Yeah, so the dimension of the PDE. And the same is then true also for the finite differences. So this gives you a way of computing finite differences, which we all know they suffer extremely from the curse of dimensionality if you solve them in the usual way. But if you do it with branching diffusions, you can solve finite differences in high dimensions. There's a caveat. So the diffusion needs to play along because you need an interpolation operator, and working with that in very high dimensions can be tricky. But you can go to dimensions like 7, 8, 9, and if you have a very nice diffusion, then you can go to very high dimensions. So we have a few examples on that ready, just not written up yet. Another thing which I like, due to the way that these branching diffusions work. So usually when you do finite differences, right, you want to do it on, let's say, R2. What you need to do is you go to a subset of R2, and then you have to impose artificial boundary conditions on your subspace, where you want to solve your finite difference scheme. And since these branching diffusions, they always run up to time capital T, you don't need to do that. You just start your diffusion somewhere, let it branch, but you don't really care where it ends up at time capital T. So the point being, just by construction, basically, if you look at the finite difference situation, then you don't need to impose artificial boundary conditions, which is quite nice because there's no, you don't create any bias doing that. Other than that, as I said, we're still in the process of exploring everything. and yeah, writing everything up. We have a few things proved, and it looks very, very promising that we can weaken a lot of the very strong assumptions. Yeah, so instead of solving the PDE, you solve the finite difference approximation, and good enough. Yeah? Especially in very high dimensions, right? Good enough. Yeah, so summing up, what I've shown you is what I think is a very, very nice and very clever way of rewriting a Feynman-Katz representation in terms of branching process. And this gives you an alternative view on probabilistic representations of PDEs. Yeah, in itself, this is already a very interesting result. And if your PDE is nice enough, if your data is nice enough, you get great numerical schemes, yeah, which is good to have in your toolbox, yeah? And nice to know about. Yeah, we have these very strong assumptions, but I still see many cases where this could be a feasible method, just like the example, yeah, that I've showed you. Or if you look in the other papers, they also have very interesting numerical examples where this really works, yeah, despite the strong assumptions. And these are non-trivial examples. Yeah, so there are where you don't have a go-to method to compare it to. Yeah. And yeah, so we're still thinking about extensions. I gave you a little bit of an outlook on where we are, which direction we are thinking. And since I know that you have so many PhD students attending here, if you think this is interesting, go have a look at it. Look at the papers, which I mentioned earlier, and come up with your own ideas. You know a lot about stochastic numerics, so I'm very sure you have great ideas on how to make this more efficient. Yeah, so feel free to join us on this journey of branching. And thanks for listening.
Thank you very much for this very nice talk.
Thanks.
I think we have time for one question. And Fabio? Yeah. Sorry.
Hello, thank you for a very nice talk. I have a question on the structure of this nonlinear term that you have considered, F, in particular, the role of delta.
Just in general, the role. Yeah, I can hear you. Just
yeah,
in general, the role.
Yes. I mean, if I understand correctly, this nonlinear term is nonlinear in U and depends on the nearby point. Maybe I missed something at the beginning of the talk on the.
Yeah, so we basically have it here, right? So let me maybe start. So the
okay.
branching diffusion, yeah, your branching diffusion
okay.
business.
Delta is a random variable, so you are essentially taking an integral over.
Yeah, integral over RD, and then C U T X plus psi d psi. That's what you do. Yeah, so you have to evaluate it everywhere. And this non-local part is assumed. I'm missing the I. This non-local part is assumed to be, it is analytic in this non-local part. Yeah, so the starting point of this thing was nonlinearities like this. So you just have the function u evaluated at tx, and those were considered to be of the form ci tx and then utx to the power I. So analytic in that variable. And our contribution is really just observing that, well, you can also do that non-locally. Yeah.
So whenever you branch, you also draw the delta.
Yeah. Yeah, exactly. So yeah, you have a jump in your branch. Yeah, so originally for these equations that you see up here, you look at where your diffusion is at the moment of branching, and then in that particular point you restart it. The only thing that we do differently is we draw delta, make that jump delta, and then start a diffusion from there. That's all you need to do to make that work.
All right. So with that, I want to thank both Christoph and Nisar for their great talks. And I think we should probably continue at 5 minutes to 4. Is that? Okay. So maybe 10 minutes break. Yes. Okay. Thank you very much.
Thanks.